Hello, I'm Liz, and I'm going to be doing exam 3 for Transport 2, and this is the first part, which is to explain the Lewis relation. So the Lewis relation is the relationship between the mass transfer coefficient and the heat transfer coefficient, and how that relates to the Lewis number. So let's just kind of get into it. So first, I'm going to just kind of write equations that include the mass transfer coefficient and heat transfer coefficient. So we have the convective heat transfer, which is equal to convective heat transfer equals the heat transfer coefficient times the temperature at the surface minus the temperature of the surroundings. And then we also have our molar flux equation, represented by a capital N. So that is going to equal our mass transfer coefficient times the concentration at the surface minus the concentration at the surroundings. So you can see that there's some parallels between like the structures in these two equations. And you can also see that we have our heat transfer coefficient and our mass transfer coefficient, and that's what we're trying to find the relationship between. So next we can also look at the Sherwood number. So we did the dimensional analysis for the Sherwood number during the second exam. And that's how we got that equation where it's coefficient A times the Reynolds number to the power B times the Schmidt number to the power C. So we're going to look at that, and we also know that the Sherwood number is equal to the mass transfer coefficient times the mass diffusivity, times the diameter over the mass diffusivity. And then, like I said, that equals coefficient A times the Reynolds number to the B power times the Schmidt number to the C power. And then we can also look at the Nusselt number because it's really similar to the Sherwood number because it equals the coefficient A times the Reynolds number to the B power, and the only difference here is it's times the Prandtl number to power C. And the Nusselt number is the heat transfer coefficient times the diameter over the mass diffusivity. Or, I'm sorry, it's not over the mass diffusivity, it's over the thermal conductivity. Okay. Great. So we can see here that we have once again, our mass transfer coefficient and our heat transfer coefficient in these equations. And we also know that the only difference in these equations here is the Schmidt number and the Prandtl number in that equation. So we can manipulate it to get the relationship that we need. So let me make sure. Yep. So if we do the Nusselt number over the Sherwood number, then we get, let me just write this out. So this is putting the Nusselt number of the Sherwood number. And we can see that the diameters are going to cancel out. So we are left with the heat transfer coefficient times the mass diffusivity over the conductivity, K. And we can also see, like I said, when we look at those Schmidt and Prandtl's number, we know that if we put this over this, then the A and Reynolds to the B are going to cancel, and then you get Prendel to the C over Schmidt to the C, so it's going to look like this. So now, let's go ahead and dive deeper into the Schmidt and Prendel number. So Schmidt equals the viscosity over the density times the mass diffusivity. Sorry if there's a bunch of voices in the background. I live with a lot of girls. So let's see here. Then we have the Prendel number, which is equal to the viscosity over the density times the thermal diffusivity, alpha. So if we relate this to the kinematic viscosity, which is viscosity over density, then we can replace that into these two equations so that we can relate them to each other. So as you can see, the Schmidt number would then equal the kinematic viscosity over the mass diffusivity, and then the Prendel number would equal the kinematic viscosity over the thermal diffusivity. So we can see that the only difference here is the denominator, so the mass diffusivity and the thermal diffusivity. And we know that the Lewis number is equal to the mass diffusivity over the thermal diffusivity. So if we look at Prendel over Schmidt, then it will look like this. Sorry for the squealing, I don't know what's going on. Oh, also the Lewis number, my bad, is actually equal to the thermal diffusivity over the mass diffusivity. So if we do Prendel over Schmidt, like I was saying, then we are going to, this is going to equal, sorry, this is kind of a weird way of writing it, but I'm going to kind of write it like this. So kinematic viscosities are going to cancel, and this equals the mass diffusivity over the thermal diffusivity, which is just 1 over the Lewis number. So we could write it like this, as you can see. So that means that this is going to be equal to 1 over the Lewis number to the power of C. And so we can kind of write it to freshen it up and make it look nicer, but this is all in all the Lewis relation. And we are going to dive deeper into this in the next parts to talk about how we can apply it to moist air and to find relative humidity in a wet and dry bulb situation. So I'll just finish writing this out and then we can move on to the next part. There we go. And then, like I said, there are specific numbers that these numbers equal in the moist air situation. So I'm just going to move on to cut here and then move on to that part in a second. Alright, so like I said, for this next part, we're going to be talking about the wet bulb, dry bulb situation to determine relative humidity. And we are going to write this relationship out in terms of pressure for this part. So basically, in the situation, you have two thermometers, one with a wet bulb, one with a dry bulb, and if there's a system with less than 100% humidity, then the water in the wet bulb will evaporate, and the heat of vaporization will cause the reading to be below ambient temperature. But the dry bulb, there's no water evaporating or anything, so it's going to give an accurate reading. So then you can use the difference between the two temperature readings to get the relative humidity. And so yeah, and in general, the greater the difference between the temperatures, the lower the relative humidity. So in this situation, we obviously have moist air, so air with water in it. And excuse me, I have the hiccups, silent hiccups. Anyways, so we have moist air, and we have some values for moist air that we can use to determine the Lewis number for moist air. So I'm just gonna write those out. Why is my pen not working? There it goes. Moist air. So we have, we have our thermal conductivity, density, specific heat capacity, and what's the last one? Mass diffusivity. So thermal conductivity is equal to 0.03. There we go. Watts per meter Kelvin. And then the density is going to be equal to 1.2 kilograms per meter Kelvin. Meter cubed. The specific heat capacity is going to be equal to 1,000 joules per kilogram times Kelvin. And then the mass diffusivity is 3 times 10 to the negative third meters squared per second. So those are just values that I memorized, but we'll kind of use those later. So next we're going to talk about kind of the definition for the thermal diffusivity, and that's equal to the thermal conductivity over the density times the specific heat capacity. So this is kind of the definition, it is the definition of the thermal diffusivity, and the reason why I bring this up is because we know in the Lewis, for the Lewis number, the thermal diffusivity plays a part in that. So we can go ahead and write that out. This is from the part 1. So the 1 over the Lewis number equals the mass diffusivity over thermal diffusivity. And so now we can plug in that density times specific heat capacity, and I'm going to call this, kind of from here on out, I'm going to call this volumetric heat capacity. Because it's the density times the specific heat capacity, so that's going to be volumetric heat capacity. And so we want to incorporate this into this equation here. So the since alpha's on the bottom, we're going to flip it and then multiply it. So this is going to equal the mass diffusivity times that volumetric heat capacity over the thermal conductivity. So next, we would plug in the variables for the moist air, but I'm not going to plug them all in. I wrote them out over here, and I know after, if I would have plugged them all into this equation, I would get approximately 1. So 1 equals that mass diffusivity times, sorry, like I said, I'm having some like hiccups, times the volumetric heat capacity over the thermal conductivity. Sorry, my pen's being kind of like laggy and choppy for some reason. But anyways, that's going to be approximately equal to 1. So we can write that like the 1 over the Lewis number, so that C power is approximately equal to 1. So let's see here. Next, we can, let me come through this next. We want to kind of isolate, we know that since this is going to be equal to 1, then the mass diffusivity over the thermal conductivity is going to be equal to 1 over the volumetric heat capacity. So that way we'll be able to look at the relationship between the Nusselt and Sherwood number and kind of isolate the heat transfer coefficient and the mass transfer coefficient, and show how that relates to the volumetric heat capacity. So let me go ahead and write out the Nusselt and Sherwood relationship that we found in part 1. So that's going to be equal to, from part 1, we have the heat transfer coefficient times mass diffusivity over the conductivity times the mass transfer coefficient. So now we can use this equation here and plug in we can plug it in so that we can get H over Kc, so the heat transfer coefficient over the mass transfer coefficient. So if we just look at and we know that this is about equal to 1. So if we, wait, let me think about this for a second. Yeah, so then the mass diffusivity over the conductivity equals 1 over the volumetric heat capacity. So if H over Kc times 1 over the volumetric heat capacity equals 1, then you can just multiply the 1 by the volumetric heat capacity, and then you end up with with the heat transfer coefficient over the mass transfer coefficient equaling the volumetric heat capacity, like that. So now we have that relationship that we can use, and that will help us find the relationship for the relative humidity. So next we need to, like I explained in the situation, there's this heat of vaporization term that we need to incorporate. So we can set the equations that utilize the heat transfer coefficient and the mass transfer coefficient equal to each other, and then look at the units, and then we'll notice that we need that extra term. So I'll kind of show that out here, but let's go ahead and write those two equations. So we have mass transfer coefficient times the molar concentration at the surface minus the molar concentration of the environment equals the heat transfer coefficient times the temperature of the environment minus the temperature of the surface. And now we can, like I said, look at the units to determine kind of like what's missing. Mass transfer coefficient has a unit of meters per second. So I'll write it like that. And then the molar concentration is going to be moles per meter cubed. And then the heat transfer coefficient is watts per meter is watts per meter squared Kelvin, and then temperature is obviously Kelvin. So our kelvins are going to even out or cancel out, and then we're going to end up with watts per meter squared on that side. And then over here we are going to end up with moles per meters squared second. And we know that that doesn't equal watts per meter squared, so we need to add something that will make it equal that. So we know that a watt is joules per second, so what we need to cancel it out is joules per mole, because then we can cancel out the moles, and then we'll have joules per meter squared seconds, which is the same thing as watts per meter squared. So we can add the heat of vaporization term onto that side, because that has a unit of joules per mole. So then it will look like this. And then our moles will cancel out, and so then we will have the correct units. So So we know that that is where the heat of vaporization term goes. So let me scroll down a little bit. All right, so then we can use that relationship that we made to then incorporate the volumetric heat capacity into this equation. So next we are going to we can like subtract, or sorry, struggling to say the right words today. We're going to divide the heat transfer coefficient by the mass transfer coefficient, so move the mass transfer coefficient on the other side, and then you will end up with this. And like I said, we made this relationship here, so now we can plug that in, the volumetric heat capacity. And now we have that correct equation there. So, like I said, we're going to be doing this in terms of pressure, so I'm going to use the ideal, sorry, I'm getting a million text messages. I'm going to use the ideal gas law, and we'll be able to get the equation in terms of the pressure. So, let's see here. We have the concentration. So if we just kind of manipulate the ideal gas law, like we've done in the past, we'll get that the pressure of the water at the surface over the gas constant times the temperature at the surface equals that concentration. And then same thing for the next concentration, so the pressure of the water in the surroundings over the gas constant times the temperature of the surroundings. And then we can also do this for density, so the total pressure over the gas constant times the average temperature. So then, let's see, so then we can assume actually that all of the temperatures are about equal to each other, because we're using Kelvin, so we can make that assumption that they're not all that different. So when we make that assumption, if we plug all of these values back in, then it will look like this. You can just pick one of the temperatures. I'm just going to pick average for the overall. I was just copying and I wasn't even paying attention. Erase. This is going to be cool. So then all of our gas constant in temperature is going to cancel out, and then we'll have a much simpler, prettier equation. So it's going to end up being the heat of vaporization times the pressure of the water at the surface minus the pressure of the water of the surroundings equals the total pressure times the specific heat capacity times the change in temperature. So that's all for the second part, and then we will move on to the third part in a second. Alright, so for the next part, we're switching gears because this is a whole new problem involving a cooling tower. So I drew out my little depiction of a cooling tower. We have water coming into it at a specific temperature, and it passes through a cooling packing material that's going to be represented by our specific area, which is meters squared over meter cubed. That's what I've highlighted in there. And then the water exits at a temperature that's cooler. This is a cooling tower, so we know that it's cooling because it's a cooling tower. And then the gas is going up through the tower, so in the opposite direction, and it enters at a temperature and exits at a temperature. And the gas involves the air and the water vapor in the air. The position along the cooling tower we are representing by Z. So Z equals 0 at the top of the tower, so you're moving in the positive Z direction going down the tower, and we're analyzing over a change of position dz. So yeah, that's the picture. And then I also defined G as the mass flow rate of the gas. So kilograms of, I guess I should say, not necessarily air, but just because it might be confusing because there's water vapor in the air. So I'm going to say gas. And then the liquid is kilograms of water, liquid water, per meter squared seconds. So L is the mass flow rate of the liquid. And then for our problem, we are deriving the differential equations for the change in the molar fraction of water throughout the cooling tower, the change in temperature of the water throughout the cooling tower, and the change in the temperature of the gas throughout the cooling tower. So first, let's go ahead and get started. We have the change in the molar fraction of the water throughout the position of the cooling tower Z. So first, let's start with I want to remind everybody, actually I'm going to write this up here, remind everyone that G is both the air and the water in the air, so like the water vapor. So I know it gets confusing with waters and liquid and all of that, but I just wanted to define that because basically we want to start creating this equation with the gas mass flow rate over the molecular weight because, we're doing it over molecular weight because we are looking for the mole fraction, looking to use the mole fraction, and since we have the mass flow rate, we're going to do the mass flow rate divided by molecular weight, and that will give us the molar flow rate. So we want to then multiply the moles by the mole fraction of the water so that we can get the amount of water in the air. So let's multiply that by the molar fraction like I said, and then we're going to multiply that by the cross-sectional area to kind of eliminate our meters squared term on the denominator. And this is all over a cross-sectional area. And we're doing the change in that. So next we are going to set that equal to the negative because it's flowing in the opposite direction. The negative molar flux of the water. So the mass transfer coefficient times the molar concentration at the surface minus the molar concentration far from the surface or the interface. And then this times the cross-sectional area times the specific area times dz. So if we do cross-sectional area meters squared times the specific area, then you get per meter, which we're looking across the position in meters. So we can actually just simplify this. I already verbally said it, but I guess I could have just skipped to writing it this way, but that was just a nice refresher of what molar flux is. So this is the molar flux of the water. So let's rewrite this to make it a little nicer. You can pull, first of all, cross-sectional areas are going to cancel when we simplify this. We can pull out the gas flow rate per molecular weight out of the differential because it's not going to change that much throughout the cooling tower, so we can assume that it's approximately constant. So that's going to look like this. So now we have our change in the mole fraction of the water, which is what we're looking for. And then we can do negative molar flux of the water times the specific area times dz. And we want dy dz, like we said. So let's just go ahead and divide what we need to, and we'll have our equation. Alright, yep, that looks right. So I'm going to circle that for our first equation. So next we are, let me make sure okay. I know that my head covers up like right here. So I want to make sure that I don't start writing into my video. Alright, so for the, let's see, where was I? For the second equation, we are looking at the change in the temperature of the water throughout the cooling tower. So for this one, we're looking at the change in enthalpy because, as we know, that involves the change in temperature in the equation. So let's write out our enthalpy of the water equation. So, like I've said before, I just like to remember MCAT, and that helps me, but obviously we're using more variables here, more specific variables, but anyway, so let's see here. We're going to do the mass flow rate of the liquid times the specific heat capacity of the liquid. Times the change in temperature of the water. And then, oh, I know, it looks like I'm missing something. And then the cross-sectional area, we always do. And then we're going to subtract the, oh, I remember. We're going to subtract well, this is equal to, sorry, I'm thinking, it's getting late. So this is equal to, that's the enthalpy change, and that is going to be equal to the convective heat transfer minus the heat of vaporization, or the heat that is absorbed when the water evaporates. So for convective heat transfer, we have the heat transfer coefficient times the temperature of the temperature of the gas minus the temperature of the water, minus the heat of vaporization times the molar flux. Wait. Heat of vaporization. Yeah. Times the molar flux. Of the water. And that makes sense because that's going to be enough. Okay. And then all of that's going to be multiplied by the cross-sectional area times the specific area times TC. Yeah, that looks right to me. So now we have our change in temperature of the water, and we just need to divide dz, do a bunch of simplification, and then we can move on to the third one. So, alright, so the cross-sectional areas cancel out. Oops, cross-sectional areas cancel out. Then we can move this over here, so we'll have sorry, I think I'm just like making this overcomplicated, so I'm just gonna do what I would do. So, it's just gonna be sorry, I'm tired. Okay. Now it's on typing. A over LCL times, I think I was stuck on like when I was practicing this, how I was formatting it, but it doesn't, it's gonna look like this. And equal to C. Alright, so that's the simplified when we get it down to the change in temperature of the water throughout the cooling tower. Alright, so then for our last equation, we are looking for the change in temperature of the gas over the change in temperature of the gas along the position in the cooling tower. So to do this, we can remember that this is steady state. So the change in enthalpy, the enthalpy of the gas is going to equal the enthalpy of the water. And we did enthalpy of water in the second, for the second equation here. So we can do the change in enthalpy of the gas and then equate it to the enthalpy of the water from the second part, and then solve for the change in temperature of the gas throughout the cooling tower. So yeah, and then that will be our equation. Sorry, this part requires some thinking for me. So this is going to be equal to our cross-sectional area times the gas mass flow rate times the specific heat capacity for the gas times the change in temperature of the gas, and then that plus the plus the heat of vaporization, and we're doing plus because it's the opposite direction. It's opposite than for the water. So that, and then we want to get the amount of the gas, of the water in the gas. So the gas mass flow rate divided by the molecular weight to get the moles times the molar fraction of the water. Yeah. And then that times the cross-sectional area as well. So then we just have to set this equal to the enthalpy of the water. So I'm going to rewrite this. And then I'm going to rewrite this is what I'm rewriting. Oh, I just realized my head's going to be in the way. There you go. What was it? Minus. Alright. Oh, I did need that. Okay. So then we can pull out, we can distribute this across what is changing. Oh, this does not need to, this is why I wrote a weird sorry. This is the change in the temperature of the gas, so this doesn't need to be here because I'm going to distribute it out. So, and then, so the temperature of the gas changes, and then the mole fraction of the water changes, but everything else we can assume is constant. And then also we know we can pull these out and cancel them. So this is going to simplify to the gas mass flow rate times the specific heat capacity of the gas times the change in temperature of the gas. And I'm also going to pull over the DC, divide the DC. Same thing over here. And then just copy all this down again. Area to, sorry, it was kind of weird way to write it. Alright, so next we can look at this term, because remember how we solved for it in the first part. We can now replace it with this, which is super convenient. So let's copy that down here. So we have now, these are going to cancel when you multiply them together. So let's rewrite everything with that. Sorry, I don't want to do too many steps at once because I don't want to make a mistake. So this is now going to be a negative sign. And then it's just going to be the molar flux of the water. Oh, and also the area, the specific area. And I totally recognize that sometimes I make the heat of enthalpy this way and sometimes I make it this way, and I just can't remember which way it is, and so I apologize, but I mean the same thing. Alright, so we're getting there. So now we can add, I'm gonna distribute the A term, the specific area, here and here. So now we can add that, and if we add it, then they actually cancel out. I hesitated because I was like, is it really that simple? But it is. So now we have this equals this. And this is what we want to end up with, our change in temperature of the gas throughout the cooling tower, which is equal to the specific area times the heat transfer coefficient over the gas mass flow rate times the specific heat capacity times the temperature of the gas minus the temperature of the water. Ooh, okay. I think I'm gonna have to do the next part at a different time because it's getting really late, but I will get that done as soon as possible and we'll move on to the next part. But this is the 3 equations that we'll use to solve in the coding part of the next part. Alright, so next I'm going to be doing the coding part. So this is B2 for the exam. So we're going to solve the differential equations that we just derived in the last part for a 20-meter tall cooling tower where the air-water heat transfer coefficient is 10 watts per meter squared Kelvin, specific area of 5 meters squared per meter cubed, and the hot water enters from the top at 70 degrees Celsius with a flow rate of 0.5 kilograms per meter squared seconds, and air enters from the bottom with a velocity of 5 meters per second at a temperature and relative humidity of 25 degrees Celsius and 50%, respectively, so 50% relative humidity. And then we're going to make plots of the water temperature, air temperature, and water partial pressure as a function of position in the cooling tower. So first we have our pretty much the same imports that we normally import when we're coding for all these transport 2 problems that we've been doing. So we're going to import numpy as np. We always just call it np so that we don't have to type out numpy, but numpy allows us to, it's a package in Python that allows us to do more complex functions. Then we're going to import make subplots from plotly.subplots to allow us to make our plots of the temperatures and the partial pressure. Then we're going to import plotly.io as PIO. Again, we're calling it PIO so we don't have to write out plotly.io. And then we also are going to set our default plot template as the dark theme, so that plotly.io allows us to change what our plot looks like. So we're setting it to plotly dark. And then from Skype.integrate we're importing solve IVP, and from Skype.optimize we're importing root. So solve IVP and root are 2 functions that we're going to need to use to solve the problem, to solve our differential equation. So IVP is the initial value problem, and Skype is just a package that allows us to do more complex calculations. Alright, so I started writing out the variables that we have that are either just like known variables or given in the problem. So we have H equals 10 watts per meter squared Kelvin. This is the heat transfer coefficient, which is given to us in the problem. Then we have the gas constant, and this is 8.314 since we are using the joules per meter Kelvin gas constant. Then we have the density of the air, which is given in the problem, which is not given in the problem, but it's just a known value. So we know that the density of air is 1.2 kilograms per meter cubed, so that doesn't change. Then we have the specific heat capacity of air, water as a gas, and water as a liquid. So these are all in joules per kilogram Kelvin. And these are also not given in the problem, but also can just be found online or in the textbook. I'm not going to write this for all the lines, but that applies to these three. And then we have the heat of vaporization, or the enthalpy of vaporization, for water, which can also just be like looked up and Googled. So this one's given in the problem, and then these are just known variables that we typed out. Okay. So then this is the specific area, which is given in the problem. And then we have molecular weights for water and air that we'll need to use in our calculations, which you can see that we use those in our calculations in the last part. So the molecular weight of water is 18 times 10 to the negative third kilograms per mole, and the molecular weight of air is 29 times 10 to the negative third kilograms per mole. And then we also have our velocity, so that's given in the problem, velocity of 5 meters per second. Our liquid mass flow rate, which is 0.5 kilograms per meter squared second, and our pressure, which is 1 atm, but that's equivalent to what we have here, which is 100 and 1,325 pascals. So we need to add a couple of things to these variables to be able to have all of our variables defined to solve the problem. So we are going to need to define our mass transfer coefficient, and for that we can look at our notes from the first part of the problem. So this was from part A when we were discussing what the Lewis relation was, and that is the heat transfer coefficient over the mass transfer coefficient equals the volumetric heat capacity, which is the density times the specific heat capacity. So Kc, if we move, you can't really see my mouse, but if we move Kc, the mass transfer coefficient, over and then divide by the volumetric heat capacity, then you get the mass transfer coefficient equals the heat transfer coefficient divided by the volumetric heat capacity. So let's do that. Equals heat transfer coefficient, which we already defined, so that's 10, divided by the density, so rho air, that's what we called it, times the specific heat capacity of the air. So C air. Cool. And then now that we have that defined, what else do we need to add? So did we have that height? No, we haven't added the height yet. So we also need to add the height, which is 20 meters. Because the cooling tower is 20 meters tall. And then we're going to have to make our z-plot. So this height is our like max z, and we want to have a bunch of z points because we're plotting the water temperature, air temperature, and water partial pressure as a function of position, and the position is represented by z. So let's make a bunch of points by calling on numpy.linspace, and then it's going to be start, stop, and the number of points that we want. So linspace returns evenly spaced numbers over a specified interval. So we're going to do 0 to height, and we're going to have 21 evenly spaced variables. And then after that, we only have a few other things that we haven't taken into consideration yet. So we have that the hot water enters at 70 degrees Celsius, and the air enters at a temperature of 25 degrees Celsius. So let's write those down. So temperature, we can call it temperature water feed equals 70 degrees Celsius, and we're actually going to add 273.15 because we want it to be in Kelvin. And then we also have the air feed temperature at 25, right? Yeah, 25. And we're also going to add 273 to that, 273.15. All right, and then what else do we need to add? We need to so I think we're good on variables, but we're going to need to consider the 50% relative humidity, and other than that, I think we've considered all of the variables. So next we're going to add some code, and we're going to add it up here because we're going to define a function that we're going to call on with our input variables here. So define, and here we're going to use the Antoine equation to find the saturation pressure. You can see my cat and my roommate are hanging out with me. Also, if I'm looking down here, it's because that's where my face is. But anyways, so we're going to find the saturation pressure based on the Antoine equation, and I actually Googled the Antoine equation, and so I already have the tab pulled up. And I also found the coefficients, the ABC coefficients in the Antoine equation for water below the normal boiling point, so I'm going to input those in a second. But first we just need to name it, so I'm just going to name it PV for vapor pressure, because the Antoine equation is the expression of the relation between the vapor pressure and the temperature of the substance. So, what is that? There's a weird noise happening. Vapor pressure, and then we're gonna make that in terms of temperature because it's at a specific temperature. And now we're just gonna input our variables. So A equals, and they're right here. So A equals 8.07131. B equals 1730.63, and C equals 233.426. And then the Antoine equation, we want to return the pressure, and since it's log P equals A minus B over C plus T, we want to do 10 to the power of everything on the right to get our pressure. So return 10 to the power of 10 to the power of A, I guess I'll put this in parentheses, A minus B over C plus C plus T, and we are going to subtract 273.15 because the Antoine equation does it in terms of Celsius. And then wait, let me just make sure. Yeah. And then hold on, it's probably written in here somewhere. The pressure is in terms of mmHg, so we're going to want to take all of this and divide it by, let me think about this for a second. I'm going to put the parentheses out here. So this is just going to be converting our pressure to pascals. So to get it from mmHg, which is millimeters of mercury, to atmospheres, we need to divide it by 760 and then multiply by 101,325 to get it to pascals. So then I'm going to shift enter there, and then now we can utilize the vapor pressure term that we just created to define what the mole fraction of the feed is. So it's going to be 0.5 because it's 50% relative humidity times that vapor pressure that we just derived from the Antoine equation of the temperature of the air feed, and then divided by the pressure P. All right, and then next we are going to make an equation for the gas mass flow rate of the air. So I'm going to call that capital G air, and that's going to equal the pressure times the molecular weight of the air divided by the gas constant times the temperature of the air feed, and then all of that times the velocity. Let's get back to our problem so that I can check that. Times the velocity, yes. Cool. And then our last couple of things here, before we start solving our differential equation, is we need to make a couple of guesses for our mole fraction, that's exiting, and then the temperature of the gas that's exiting. So let's do y exit guess equals the feed mole fraction of air times, let's just do 1.1, and then for the temperature exit gas, let's do the temperature of the air feed plus 5. So now we can move on to solving our differential equations now that we have defined all of our variables and found the pressure and found the pressure for the from the Antoine equation. Alright, so I'm gonna run this. And it's saying, it says that A is not defined, and that's because it should be A. Actually, I'm gonna make all the errors A's so that I don't get confused. Let's rerun that. Alright, now we got a green check, so we're good to go. So I'm gonna shift enter to make a new code. So first we need to define our gas mass flow rate, G, and G equals the gas flow rate of the air in the gas plus the mass flow rate of the water in the gas. So we need to, since we don't have the water in the gas defined, we need to do that. So GW is for the mass flow rate equals Y, the mole fraction, divided by 1 minus Y, because it's just because we know that the two mole fractions are going to be equal to 1, and then that times the mass flow rate of the air in the gas, so G air, or actually we made it A now, so all the airs are going to be A's since I made all the waters W's. And then just multiply that by the amount, so the molecular weight of the water over the molecular weight of the air. And then, like I said, we're going to do the mass flow rate of the gas equals GW plus GA, like I explained before. And then we need to do our average molecular weight. So that's going to be equal to the gas mass flow rate divided by the air in the gas divided by the molecular weight of the air plus the water in the gas divided by the molecular weight of the water. My typing skills are off today. Oops. Alright, so name Y is not defined. Oh, is my audio? Yes, okay. So the reason for that is because, so all of these variables need to be inside of a function. I'm going to call the function dyTgtw because those are the values that we're looking to get out and plot. And this is going to be in terms of our z variable, the position along the cooling tower, and then v is going to be our 3 output variables that we're going to plot. And we are going to define those, and that's where the y comes in. So I'm going to move these over, and then y is going to be equal to the first value in that array. So we're going to do b as 0 because 0 is the first value. Then tg is going to equal, actually, I think, were we doing water first and then, I mean, I know it doesn't matter, but yeah, so let's do this so that we're staying consistent. So TW, so temperature of the water, equals V of 1, and then the temperature of the gas equals V2, the third item in the array. So now we have defined our y variable, so that should be all good to go. So next, before we type out our differential equations that we found in the last part, we can write out our molar flux of water equation and the specific heat for capacity for the gas. So the specific heat capacity of the gas is equal to the specific heat capacity of the air times the mass flow rate of the air, and then plus the heat capacity of the water vapor, so like the water and the gas, times the mass flow rate of the water and the gas, so GW, divided by, all of that divided by the overall mass flow rate of the gas. Yeah, that looks right to me. And then we're going to define our molar flux, so of the water, so NW equals the mass transfer coefficient divided by the gas constant times the temperature of the gas, right, RT, yeah, and then that times the vapor pressure or the saturation pressure of the temperature at the temperature of the water minus the mole fraction times pressure P, the 101,325 pascals. Yes. Now we can start writing out our differential equations from the last part. So here's the one note from what we were writing on before. Make this a little bigger. Let's go to part 3. What is happening here? Why did it cut out? Oh, okay. So we can just write these out. So first we have our dy dz, which is the change in mole fraction throughout the position of the cooling tower. So I'm just going to call that dy equals negative the specific area times the molecular weight, the average molecular weight, which we defined, times the molar flux, which we defined, and then all of that over the gas mass flow rate. So all of those are defined, so we're good on that. Then we have d2w, which is the change in the temperature of the water throughout the position of the cooling tower, and that's going to be the specific area divided by, the liquid flow rate, which we defined in the variables up here, which we were given in the problem, which is 0.5 kilograms per meter squared seconds, times the specific heat capacity of the water, the liquid water. Did I find that somewhere? Oh yeah, I did. I'm going to do lowercase l to keep it consistent. There we go. And then this needs to be over that, like that. And then, actually, I just want to make sure my parentheses are correct, so I'm going to add extra ones. Then we're going to multiply all of that by the heat transfer coefficient times the temperature of the gas times the temperature of the gas, which is the air feed, minus the temperature of the water, water feed, and then minus the heat of vaporization, which is the HV, times the molar flux. Oh, that was a doozy. All right. I think I got my parentheses all correct here. Oh, this is supposed to just be TG and TW. I forgot that I defined these up here. So that's why I was confused. And I was doing the feed because I was like, we don't have any other temperatures defined, but we do now. I thought that would be incorrect to use the feed. So we are going to use the temperature of the water and the temperature of the gas. That's going to be our variables within this function here. Alright, next we're going to do the next, so we did dy, we did dtw, so finally we're going to do our third differential equation, which is, if it lets me scroll, there it goes, sometimes OneNote gets stuck, dTg, which is the temperature of the gas. And that one is just the specific area times the heat transfer coefficient divided by the gas mass flow rate times the specific heat capacity of the gas, which we defined above, so we got that. And then those, that times the Tg minus Tw, the temperature of the gas minus the temperature of the water. Alright, so next, let's shift enter to make sure we don't have any errors. Good. We got a green check, that's always good. And we're going to return dy dtw and dtg. Our three are what comes out of those three equations. Alright, so next we're going to nest this inside of another function, which, so we can indent that over, and we're going to call this one converge feed air T y for temperature and mole fraction. And then we're going to use variable B2 instead of B, just our new variable here. And then, oh, I can probably minimize this now. So let's see, what I'm missing a colon here. So now our y exit is going to be, so the mole fraction at the exit is going to be equal to the first item in that array, the B2 array. Then our TG exit is going to be equal to the second. Which is 1. And then I'm going to call the solution sol, and so now we're going to solve the IVP. So sol is going to equal solve IVP for the initial value problem, And as you can see, we have function, t-span, why not, the method, and we're going to do dense output. So the function is the dy tw tg, or is that what I call it? Yeah, tg. And then the oh, I need to look at the screen more. The t-span is going to be from our 0 to our max height, which is 20, which is given in the problem. And then the y naught is going to be our values that we're looking for here. So the y exit, the tg exit, and TW feed. And then we're going to do method equals redow, just because that's our favorite for some reason, and dense output equals true, so we can solve at any point, any z position. Dense is the underscore output. Output equals true. All right. So we're getting there. All right. So next we are going to do what's going on here. Oh, I think this. Alright, so let's do our return and see if that kind of solves the error. So we're going to return the solution from 0. So for our whole list, so you can do -1 to get to the last value, and then minus the y feed, the mole fraction of the air in the feed, and then the solution from 2 to -1 minus the YA or TA, potential there, feed. Oh, and this needs to be dot. Wait, let me see this. What if it's not defined? It's right here. What are you doing?
Okay, I should go back to my room.
Why?
I need like my desk set up.
I understand.
So
You
I
want
can't
to
concentrate.
sit here?
I don't know. It's just like in a corner. Like I feel like I need like a whole.
And your desk isn't in the corner?
Oh,
With
like
a drawer falling
it's
into
kind
your
of
lap?
claustrophobic if I'm like right.
Okay, you can do whatever you want. I just think your room is hella claustrophobic. Like, I mean, not your room, but your desk
My desk
setup.
area.
Because it's, I mean, I would have rotated to give you more space. That's just me though. Because then all of a sudden your
Okay.
drawer won't fall into your lap.
Yeah. I'll test it out.
I mean, you don't have to.
I'll test it out and then if it's not working for me, I'll come back down. I don't think the problem is the desk. I think it's the desk.
Well, we'll blame it on the desk.
Yeah, I'll probably come back down to talk, but can I even talk to you?
Huh?
Can I talk if you're recording?
Um,
Are you recording right now?
yeah, but I'm gonna cut all this out.
Oh, okay. So if you're not speaking, I can come down and talk.
Yeah.
Okay.
Alright, so then we are going to do global sol, because we're about to define what our solution is. And so we need to have that in there. So sol solution to our IVP, so now we're finally going to solve these differential equations using solve IVP, which is the initial value problem. And we need to put in our function, which is dy tw dg, our t-span, which is our range from 0 to the height, our y0, which is the values we're looking for, which is y exit, tg exit, and T, what did we call it? T air feed. And then our method is Radal, just because that's our favorite for some reason. And our dense output is going to equal true. So that we can solve this along any point. And then we're going to do dot sol, then we're going to do dot sol, so we're going to solve it at each of the z plot points that we made. Z plot, there we go. So we're going to solve it along all of those points. So that looks good. Alright, next, what do we need to do next? Next we need to return our values at each of these points. So sol from 0 to the last point. So we're going to solve at all of the points, and instead of knowing how many points there are, we can just do -1. Then we're going to subtract the mass fraction, mole fraction. Have I been saying mass fraction this whole time? Mole fraction of the air in the feed, and then we also want to return the solution from 2 to -1 and subtract the mole fraction, or the temperature of the air in the feed, because the third third one that has to do with the temperature. Alright, so we're getting really close here. Lastly, we're just going to do our root solver. And because we want to find the root of our function that we just made, and then we're going to do make subplots to make our 3 plots for the air temperature and water and partial pressure as a function of position in the cooling tower. So first we're going to do root, and it's going to be the root of the function we just made, and then our initial guesses, which are y x guess and tg x guess. So shift enter there. Oh, is there, oh, I forgot a comma. Great, so the solution converged, and now we can start making our plots. So I'm going to set it as fig for figure equals make subplots, equals make subplots, and then our rows equals 3 because we have our 3 variables, and then columns equals 1. Then we're going to do fig dot scatter, or fig dot add, so we want to add our points on here, so fig dot add scatter, yep, and we're going to add each of all of our 3 sets of points. So first we're going to do the mole fraction of H2O, of water, so that's going to be x equals, so the x is going to be the same for all 3, and that's the z plot, so the x is the position in the cooling tower, and then the y is going to change. So for the first one, it's going to be y equals the solution at the first point in the array, because that's what we made it equal to for all of the points. So we can use a colon. Is it that right there? And then rows equals 1 and columns equals 1, and then name equals y H2O. And then I'm just going through this quickly so that I can make sure that I did it right. Uh-oh. Uh-oh. I have a problem with the scatter. Okay. So what I did was, sorry, I was kind of messing around with it because I wasn't exactly sure what the syntax was, but I was selecting which row I was calling on. I thought it was rows, but it's row, and calls is call. So I did that. I named it YH2O, and then for the second one I just copy and pasted and chose the second element, and then called on the second row and named it the temperature of the water, and then I'm just going to copy that and call it the temperature of the gas, and row 3 and the third element, so the second. And then lastly, kind of resize it. That's a bit long. There we go. I know I'm on half screen, so maybe it's making it look weird, but. Alright, so there's clearly a problem with these graphs, and I noticed that these values are wrong, and when it converged, and I was scrolling through it for a really long time, and I realized that I put the parentheses in the wrong spot here. Because if we're to look at the Antoine equation, it's the log of p, so you're doing 10 to the power of all of this, so that's why this is in parentheses, and then we're just converting that. So let's go ahead and rerun everything. And now we have our beautiful plots. So this makes sense. They're all decreasing throughout the position of the cooling tower, which is what we would expect the molar fraction of the water, the temperature of the water, and the temperature of the gas to do here. So, yeah. Thank you for watching.